Your water filter is rated for 10,000 gallons. That is what the box says. That is what the Amazon listing says. That is what every review site copies and pastes from the manufacturer's spec sheet without testing it. I tested 3 brands, ran clean municipal tap water through each one until the flow rate dropped below what I consider functional, under half a litre per minute. The best performer reached roughly 6,000 gallons, 60% of rated capacity. The middle one stopped at about 4,000, and the worst one, a brand with over 12,000 5-star reviews and a bestseller badge, clogged at 1,800 gallons, 18% of the number on the box. With clean tap water, not creek water, not pond water, not post-disaster turbid water. The cleanest, most pre-treated water available in a developed nation. Let me verify that spec sheet claim. It does not survive contact with reality. Last episode, we walked through your house and counted every single point of failure. 31 systems with 0 redundancy for the average household. The first upstream dependency I flagged was water. Every drink, every meal, every flush, every hand wash, one source, one pipe, 0 fallback. Today we audit that dependency, not with opinions, with chemistry, with testing data, and with 3 myths that the prepper community treats as established fact, but has apparently never bothered to verify. Myth 1. Water does not expire. Myth 2. Any filter will work. Myth 3. 72 hours of stored water is a sufficient plan. Each of these is wrong, not slightly wrong, structurally wrong. And each one creates a gap in your water system that you will not discover until you need the system to perform. By then, it is too late to fix. Let me take them apart one at a time. Myth 1. Water does not expire. You will hear this everywhere. Forums, YouTube channels, prepper blogs, even from people who should know better. Water is water, H2O. A molecule that has existed for billions of years does not suddenly go bad because you put it in a jug. Chemically, this is technically correct. A water molecule does not degrade. It does not have an expiration date in the way milk or bread does. But here is what that argument misses entirely. You are not storing molecules. You are storing a solution, water plus everything dissolved and suspended in it. Municipal tap water contains dissolved minerals, trace organic compounds, residual disinfectant, and microorganisms in concentrations low enough to be safe at the moment of filling. That solution is not static. It is a living, reacting system, and it changes over time in ways that matter. Municipal tap water contains residual disinfectant, usually chlorine or chloramine, depending on your utility. That residual is not an accident. It is a deliberate engineering control. The treatment plant adds enough disinfectant so that a measurable amount survives the journey through miles of pipe and arrives at your faucet still active. That residual is what keeps the water microbiologically safe in transit. When you fill a container and seal it, you are severing that system from its source. No more fresh disinfectant. What you sealed in starts dissipating immediately. Chlorine off-gases. It is a volatile compound. The rate depends on temperature, surface-to-volume ratio, UV exposure, and the container material. At room temperature, around 68 Fahrenheit, free chlorine in a sealed, opaque container drops below detectable levels within 4 to 7 days. That is days, not months, not years. Days. Chloramine is more persistent because it is a combined compound, chlorine bonded to ammonia. It can last weeks to a few months under ideal conditions, but it also breaks down eventually. Once the disinfectant residual reaches 0, the water is no longer actively protected against microbial growth. Whatever organisms were present in trace amounts, and they are always present in trace amounts, even in water that meets every EPA standard, now have an environment with no chemical opponent. The barrier is gone. The countdown begins. Here is where it gets interesting. I stored 6 identical 1-gallon food-grade HDPE containers of municipal tap water. Same source, same day, same containers, same fill procedure. 2 stored at 68 degrees Fahrenheit in a dark closet, 2 at 85 in a ventilated storage room, 2 at 95 in a garage, which is roughly the temperature of a garage in Arizona, Texas, or Florida in midsummer. I checked them at 30, 90, 180, and 365 days. At 30 days, all 6 samples were visually clear and had no detectable odor. You would look at them and see water. At 90 days, the 68-degree samples remained visually clear. No film, no color change, no odor. The 85-degree samples had developed a faint translucent film on the interior container walls, barely visible unless you held the jug up to a light at an angle. The 95-degree samples had visible biofilm on the interior surfaces and a slight cloudiness that was immediately apparent. Biofilm is a colony of microorganisms that adheres to a surface and secretes a protective matrix. It is the same phenomenon that creates that slippery layer inside a vase of old flowers. Except this is in your drinking water reserve. At 180 days, 6 months, the 68-degree samples still looked clear, but had a faint, stale taste. The 85-degree samples had noticeable cloudiness. The 95-degree samples had visible suspended material and an odor I would describe as swampy. Not sewage, but not anything you would voluntarily drink. At 12 months, the 68-degree samples still looked clear to the naked eye, but tested positive for heterotrophic bacteria at concentrations well above the EPA's guideline of 500 colony-forming units per milliliter. The 85-degree samples were visibly degraded, cloudy, odorous, biofilm on every interior surface, and the 95-degree samples were water you would not give to a dog. Visible particulate, thick biofilm, a smell that made me step back when I opened the cap. Water does not expire, but stored water absolutely degrades. The container, the temperature, the initial disinfectant level, and the ambient microbial load all determine the rate. And the rate is faster than most people assume because most people have never tested it. They fill a container, seal it, put it in the garage, and check it off a list. They do not open it at 90 days to look at the walls. They do not smell it at 6 months. They do not test it at 12. They trust the myth. The myth does not survive verification. Here is the IT analogy that makes this click. A database backup that you made a year ago and never verified is not a backup. It is a file on a disk. You do not know if the data is intact. You do not know if the restore procedure works. You do not know if the media has degraded. Every IT engineer knows this. Untested backups are not backups. Stored water that has never been inspected, rotated, or tested is the same category. It is a container on a shelf. It might work. It might make you sick. You will not know until you need it. The fix is straightforward and costs almost nothing. Rotation. Treat stored water like a production database backup. It is only valid if it is current and verified. A 6-month rotation schedule. Drain, clean the container with dilute bleach solution, rinse, refill with fresh municipal water, maintains the disinfectant residual and resets the bacterial clock. Mark the fill date on every container with a permanent marker. Set a calendar reminder. This is a recurring maintenance task, not a one-time purchase. Your water reserve is not something you build once and forget. It is something you maintain on a cycle, the same way you rotate backups in a data center. The moment you stop maintaining it, the degradation clock starts running and does not stop until you intervene. If you want longer storage without rotation, you add a measured dose of unscented household bleach, sodium hypochlorite, at the time of filling. The EPA and CDC both provide dosage tables. For water with no turbidity from a treated municipal source, the standard recommendation is 8 drops of 6% bleach per gallon. That extends the safe storage window past 12 months under cool, dark conditions, and it costs you about 1/10 of a cent per gallon. The information is free. The solution is nearly free. The reason people do not do it is because they believed the myth that water does not expire and never verified it. One more variable most people miss entirely: the container itself. It is not a passive vessel. Plastic containers, HDPE, PET, leach chemicals into water over time. The rate accelerates dramatically with temperature and UV exposure. PET bottles release antimony. Various plastics release phthalates, BPA, or BPA substitutes, depending on the formulation. A PET water bottle sitting in a hot car for 3 days has measurably elevated antimony levels. A case of bottled water stored in a sunlit garage for 6 months is leaching compounds at a rate the manufacturer never tested for, because the manufacturer assumed you would drink it within weeks of purchase. Food-grade HDPE containers rated for water storage and kept in cool, dark conditions are the minimum standard for any reserve beyond 30 days. Glass is better chemically, but heavier and breakable, acceptable for home storage, impractical for anything mobile. Stainless steel is best for long-term integrity, but expensive at volume. The point is this: the container is a component of the system. It is reactive. It interacts with its contents. It degrades on its own timeline. Include it in your maintenance schedule, or it will surprise you. Myth 2. Any filter will work. This one is more dangerous than Myth 1 because it creates false confidence in a critical system. The logic sounds airtight. I purchased a water filter. It is rated to remove 99.99% of bacteria and protozoa. Therefore, my water is safe. The logic is wrong because it treats filtration as a binary state: filtered or unfiltered, safe or unsafe. Filters are not a binary. They are a spectrum of performance that degrades with use, varies with source water quality, and depends on conditions the manufacturer tested for, and conditions you will encounter that the manufacturer did not. Water filters sold for emergency preparedness are rated under NSF and ANSI standards. The two relevant ones are Standard 42, which covers aesthetic effects like taste, odor, and chlorine reduction, and Standard 53, which covers health effects including lead, cysts like giardia and cryptosporidium, and specific chemical contaminants. A filter certified under Standard 53 has been tested in a controlled laboratory. Defined flow rate, defined influent water quality with specific turbidity and contaminant concentrations, defined temperature, defined pressure. These conditions are reproducible and standardized. They are also nothing like what you will encounter when you are filling a bucket from a creek after 3 days without municipal water. The rated capacity, that 10,000-gallon number, comes from testing with standardized challenge water. The turbidity, the particulate load, the chemical composition are all defined by the testing protocol. Your actual water source in an emergency will not match those parameters. Creek water carrying silt and organic debris. Rainwater that sat in a collection barrel for 2 weeks. Flood water with dissolved agricultural runoff. Each carries a particulate and microbial load that will clog or overwhelm a filter at a rate dramatically faster than the test protocol predicts. The spec sheet number is a laboratory ceiling measured under ideal conditions. It is not a field guarantee. Treating it as one is an engineering error. I tested 3 filters, all commonly recommended on prepper forums. All available from major retailers for between $30 and $65. all carrying appropriate NSF certifications. I will not name brands because this is about the filtration category, not about targeting specific companies. I ran each filter using the same municipal tap water at room temperature, measuring flow rate every 200 gallons. Brand A, a gravity-fed ceramic and carbon filter, maintained functional flow through approximately 6,000 gallons before degrading below my half-litre per minute threshold. That is 60% of its rated capacity, with clean tap water. Brand B, a pump-action filter with a hollow fibre membrane and carbon element, reached about 4,000 gallons, 40% of rated. Brand C, a popular straw-style filter with glowing reviews and a survival marketing campaign, hit 1,800 gallons and stopped producing meaningful flow. I disassembled the unit. The activated carbon was fully saturated and the pre-filter screen was caked with a fine sediment layer. Sediment that should not have been present in meaningful quantities in EPA-compliant municipal water. But trace particulate exists in all water. At 1,800 gallons of throughput, those trace amounts accumulate into a functional blockage. Now extrapolate. If Brand C failed at 1,800 gallons with the cleanest water available in a developed country, what do you think happens with creek water carrying silt, organic debris, tannins, and 10 to 50 times the particulate load? You are looking at maybe 200 to 400 gallons before that filter is a decorative tube. And here is the part that should concern you most. You will not necessarily know it has failed. A clogged filter is obvious, flow stops. But a saturated filter is invisible. The water still flows through, it just is no longer being treated. A saturated activated carbon bed does not simply stop adsorbing contaminants. Under certain conditions, it releases previously captured contaminants back into the output water in a process called desorption. The filter becomes a source of contamination rather than a barrier against it. This is well documented in water treatment engineering literature. It is not a theoretical edge case. It is a measured, published phenomenon that occurs in every carbon-based filter that is used beyond its effective capacity. The engineering solution has three components. First, pre-filtration. Run water through a coarse physical barrier before it reaches your primary cartridge. A bandana folded 4 layers, a coffee filter, a purpose-built sediment pre-filter, a slow sand filter if you have time and materials. This removes the large particulate, silt, debris, organic matter that clogs fine filtration elements prematurely. It is the equivalent of putting a CDN or a load balancer in front of your application server. The front layer absorbs the bulk traffic, so the precision backend can do the fine work it was designed for. A $1 coffee filter extending the operational life of a $60 cartridge by 5 to 10 times is not a hack. It is standard multi-stage water treatment design. Every municipal plant in the world uses coarse filtration before fine filtration. Apply the same architecture. Second, redundancy. Do not own one filter. Own at least 2 and make them different technologies. A ceramic gravity filter and a pump filter with a hollow fiber membrane. Different mechanisms, different failure modes, different vulnerabilities. If one clogs, the other operates on a completely different principle. In IT, we call this technology diversity in redundancy. Not 2 identical servers that fail from the same software bug simultaneously, but 2 different systems where a single vulnerability cannot cascade across both. Your backup filter should not be the same brand and model as your primary. It should be a fundamentally different approach to the same problem. Third, testing and monitoring. Run your filter. Not once when you buy it and then store it for 3 years. Run it periodically. Measure the flow rate at regular intervals and track it. Plot a curve if you are methodical about it. When flow drops to 50% of initial baseline, the filter is entering the zone where performance claims become unreliable. Replace or service the element before you need maximum performance from it. A filter in a sealed box on a shelf for 4 years is not a tested component of your water system. It is an untested hypothesis with an expiration date you do not know. And in this context, untested means unreliable, period. One more data point that most filter discussions overlook entirely and that matters enormously for emergency water sourcing. Viruses. Most portable filters, ceramic, hollow fiber, activated carbon, are rated for bacteria and protozoan cysts. They are not rated for viruses. The size difference explains why. Bacteria are typically 1 to 10 micrometers in diameter. Protozoan cysts, like Giardia, are 8 to 15 micrometers. Viruses are 0.02 to 0.3 micrometers. That is 50 to 500 times smaller than bacteria. Most portable filter pore sizes are around 0.1 to 0.2 micrometers, small enough to block bacteria and cysts, too large to reliably capture viruses. In the United States, municipal water is treated with chemical disinfectants and sometimes UV to inactivate viruses before it reaches your tap. So if you are filtering treated tap water, viral removal is handled upstream. But if your water source is an untreated surface supply, a pond, a creek, a rain barrel, a flooded basement, filtration alone does not address viral contamination. You need a purification step in addition to filtration. Chemical treatment with chlorine dioxide or iodine. UVC exposure at the correct dose and contact time. Or boiling for at least 1 minute at a rolling boil, 3 minutes above 6,500 feet elevation. Filtration removes particulate and biological threats above a size threshold. Purification inactivates threats below it. 2 stages, 2 mechanisms, not 1. A filter without a purification backup is a system with a known, documented gap. And now you know about it. Myth 3. Store 72 hours of water and you are covered. This is the federal recommendation. FEMA says 1 gallon per person per day for at least 3 days. For a family of 4, that is 12 gallons. 12 gallons. Let me put that number into context because the number itself sounds reasonable until you compare it to actual usage. A standard shower uses about 2 gallons per minute. A family of 4 taking 5-minute showers, not long showers, short ones, uses 40 gallons on showers alone. In 1 day. The 12-gallon FEMA reserve covers less than a third of 1 day's shower water for one family. A single toilet flush on a standard model uses 1.6 gallons. 5 flushes per person per day times 4 people is 32 gallons. On toilet flushes alone. Cooking a simple pasta dinner uses 2 to 3 gallons between boiling, rinsing and cleaning. Washing dishes by hand for a single meal uses 3 to 5 gallons if you are careful. Brushing teeth, washing hands, basic face washing, another gallon per person per day. Add it all up, and a family of 4 uses 80 to 100 gallons per day under normal conditions. 12 gallons is not a 3-day supply. It is a few hours of conservation-level survival drinking and nothing else. Now, I am not saying you need 100 gallons per day in a crisis. You do not. You cut showers. You stop flushing with potable water. You minimize everything. Under strict rationing with no hygiene, no sanitation, no cooking beyond mixing water with dehydrated food, the bare minimum for survival is roughly half a gallon to 1 gallon per person per day, depending on climate, activity level, and body mass. FEMA's 1 gallon figure is workable as a survival floor, but it assumes 3 days, and 3 days is where the recommendation collapses. The 72-hour recommendation was designed for a specific scenario, a short-duration localized event, a hurricane, a tornado, a brief municipal water main break, where government assistance is expected to arrive within 3 days. It was not designed for cascading infrastructure failures. It was not designed for grid-down scenarios where the water treatment plant loses power and cannot restore pressure. It was not designed for supply chain disruptions that stretch for weeks or months. Puerto Rico, after Hurricane Maria, 2017. The electrical grid was destroyed, not damaged, destroyed. Without grid power, water treatment plants could not operate. Municipal water pressure dropped to zero across most of the island. Restoration of reliable water service took not 72 hours, but months. Some areas went nearly a year. Jackson, Mississippi, 2022. Flooding and then freezing damaged the water treatment infrastructure. The city was under a boil water advisory for weeks. Water pressure was so low that some neighborhoods got nothing from the tap at all. Flint, Michigan. A water quality crisis that lasted years, not days. These are not hypothetical scenarios from a survival fiction novel. These are events that occurred in the United States within the last decade, to American citizens served by modern municipal infrastructure. The 72-hour window is a planning minimum designed for the best case. Engineers do not design for the best case. Engineers design for the worst case. The system is expected to encounter within its operational lifetime. If you build a bridge to handle only the average traffic load, it collapses on the first above-average day. If you size a server to handle only the average request rate, it crashes under the first traffic spike. The same principle applies here. Design your water system for the scenario that will stress it, not for the scenario where nothing goes significantly wrong. Run the numbers for a realistic minimum. 1 gallon per person per day covers drinking and minimal food preparation at survival level. It does not cover hygiene, sanitation, dishwashing, wound cleaning, or medical needs. A more honest estimate for baseline survival, not comfort, not normalcy, just functional survival, is 2 gallons per person per day. For a family of 4, that is 8 gallons daily. For 14 days, 2 weeks, that is 112 gallons. For 30 days, 240 gallons. That is 20 times the FEMA recommendation. And 30 days is still optimistic for a regional infrastructure failure, as history demonstrates. Here is how I structure water planning, and it borrows directly from IT infrastructure design. Tiered architecture with failover between layers. 3 tiers. Each tier serves a different time horizon and has a different dependency profile. Tier 1 is immediate, stored treated water in food-grade containers. This covers your first 72 hours to 2 weeks. It requires 0 infrastructure, 0 skills, 0 energy input. You open a container and drink. The cost is roughly $1 to $2 per gallon of storage capacity if you buy dedicated blue HDPE water containers. Cheaper if you sanitize and reuse food-grade containers you already own. 2-liter soda bottles work fine if properly cleaned. This tier is your buffer. In IT terms, it is your local cache. It buys you time. Time to assess the situation. Time to activate Tier 2. And critically, time to avoid making bad decisions under the cognitive impairment that dehydration causes within 24 to 48 hours. Tier 2 is short-term. Filtration and purification of available water sources. Rainwater. Municipal supply that is still flowing but under a boil advisory. Stored water that has exceeded its safe shelf life and needs retreatment, or nearby surface water. This tier requires equipment, a filter, a purification method, collection containers, and consumables that deplete over time. Filter cartridges, chemical treatment supplies, UV bulb lifespan. Tier 2 extends your water independence from weeks to months, depending on the availability of source water and your consumable stock. Equipment cost, $40 to $200, depending on quality and redundancy level. Ongoing consumable cost, $10 to $30 per month. This is your application layer. It processes raw input into usable output, but it depends on both a source and on parts that wear out. Tier 3 is renewable, a water source that does not depend on stored reserves or on consumables with a finite supply. A well with a hand pump or a solar-powered pump. A rainwater harvesting system with sufficient catchment area and storage volume for your climate and household size. Proximity to a surface water source combined with a robust, maintainable multi-stage filtration and purification system. Tier 3 is the only tier that operates indefinitely without external resupply. It is also the most expensive to build and the most knowledge-intensive to maintain. But it is the only tier where the clock is not running. Every system below Tier 3 has a timer on it. The stored water degrades. The filter cartridges saturate. The bleach loses potency. The containers crack. Tier 3 resets the timer by connecting your system to a renewable input. In IT, this is the difference between running on battery backup and running on a generator with a fuel supply chain. The battery buys you hours. The generator buys you as long as the fuel lasts. Tier 3 is the solar panel. The input does not deplete. Most prepper advice lives entirely in Tier 1. Buy water, store water, maybe buy a filter. Done. Check the box, move on. That is like building a server with one hard drive, no RAID, no backup power supply, no disaster recovery site, and calling it production ready. You have not solved the problem. You have purchased a grace period. And grace periods end. They always end. Let me bring this back to the engineering framework from episode 1. Your water system is a subsystem of your household infrastructure. Like any IT system, it has 4 components: input, processing, storage, and output. The input is your municipal supply or well. The processing is filtration and purification. The storage is your containers, tanks, and reserves. The output is consumption, every faucet, every glass, every pot, every flush. Each component has a rated capacity and a real capacity. Each has a failure mode and a failure rate. Each has a maintenance interval and a replacement schedule. And not one of them, not a single component, performs to spec sheet numbers in real-world conditions over sustained operational time. The gap exists in every piece of equipment, in every container, in every consumable. Your job is not to buy equipment and assume the gap does not apply to you. Your job is to measure the gap in your specific configuration with your specific water source at your specific storage temperature. Document it, plan around it, and maintain the system on a schedule that keeps every component inside its verified operational parameters. Not the manufacturer's parameters. Yours. Measured, recorded, updated. And here is the part that makes this actionable rather than just analytical. None of this requires expensive equipment. A kitchen timer, a measuring cup, and a notebook give you more real data about your water system than a $1,000 filter setup that has never been tested. The most expensive preparedness failure is not buying the wrong gear. It is buying the right gear and never verifying that it works the way you assume it does. Verification is free. Assumptions cost everything. Before we wrap, one observation that ties today's 3 myths together. They are not random misconceptions. They share a root cause. Trust without verification. Water does not expire, trusted by the community, never tested by the individual. Any filter works, trusted based on the spec sheet, never tested under real load. 72 hours is enough, trusted from a federal guideline, never stress-tested against historical data. This pattern is the single most dangerous vulnerability in any preparedness plan. Not the equipment, not the budget, the assumptions. In IT, we have a specific name for untested assumptions embedded in a disaster recovery plan. We call them fiction. A disaster recovery plan that has never been executed in a test environment is not a plan. It is a document. It has the shape of a plan without the substance. The same is true here. A water system you have never run under any kind of realistic load is not a system. It is a purchase history with an optimistic narrative attached to it. Here is your assignment. It takes 30 minutes and costs $0. If you own a water filter, any kind, any brand, any age, take it out. Run it. Fill the input reservoir with tap water. Time how long it takes to produce 1 liter of filtered water. Write that number down. That is your current flow rate. If your filter has already processed several hundred gallons, and if you have been using it with any regularity, it has. Compare that flow rate to what it was when the filter was new. If you never measured the baseline when it was new, you have already learned something important. You deployed a critical system without recording its initial performance metrics. You cannot measure degradation without a baseline. That is lesson 1. Now take it a step further. Mix a tablespoon of fine dirt or clay into a gallon of tap water. Stir it until the water is visibly turbid, but not thick. Pour it through your filter. Measure the flow rate again. Measure the clarity of the output. Taste it if the output is clear. That is your filter's real-world performance under mild stress. Not catastrophic conditions, not floodwater. Mild. If the flow rate dropped significantly or the output is not clear, your filter is telling you something the spec sheet did not. Drop your numbers in the comments. The spec sheet rating, your measured clean water flow rate, and your turbid water flow rate. 3 numbers. Build a community dataset. Because 100 real data points from 100 real tests in 100 different households are worth infinitely more than 10,000 spec sheets written by marketing departments who have never used their product to filter creek water at 35 degrees with numb fingers. Next episode, we go deeper on the math. A family of 4, 30 days, every use case quantified, drinking, cooking, hygiene, sanitation, medical, cleaning. Calculated to the gallon with no rounding in your favor. The total number is larger than you expect, and every gallon in that calculation depends on what we covered today. Storage that does not silently degrade, filtration that performs to tested numbers rather than printed numbers, and a plan that operates in tiers with defined failover rather than a single container and a hope. Subscribe. That math drops next week. And once you see the real number, you will never look at a faucet the same way again.